Okay, let's do some system design for the auction system. So auction system is a bidding service similar to eBay. Okay, first of all, we talk about functional requirements. So the first one would be we allow users to post one auction to the website. User post auctions. And two, we allow other users to bid for that auction. And the highest price will get the bid at that moment. Highest price wins. So whenever user is posting that auction, we would provide a start price and the end time. So when this auction will be closed. So the third one is users could be able to view the auctions, view the auction status for that item. User see auction status near real time. Okay. So we first are focusing on these three functional requirements, and let's go to the non-functional requirements. Okay, so first of all, we want high consistency whenever a user is posting an auction and bid for that auction. So we want it to be consistent. So strong consistency when post or bidding on an auction. Second of all, we wanted the entire system to be highly available. High availability. And third, so we wanted to make the prices and the auction status near real time. So also we want to be able to support concurrent bidding of 1 million per bid per auction. Okay. So there might be some other function and non-functional requirements. For example, like payments and dynamic ending the bidding instead of having a static ending time. So it's out of scope as of today's discussion. So let's first focusing on the above functional and non-functional requirements. And so as we already checked, so the bottleneck of this problem is that we're basically need to support the concurrent bidding for like 1 million of the bidding for one particular auction. So we will skip the estimation as of now, unless we need it to make some decision. Estimation. For APIs, it's very straightforward. So for the first functional requirements, it should be a post request via HTTP that gives us name, start price, and the time, user ID, etc. So the second one is another post that gives us auction ID, user ID, the price whenever a user is bidding for one auction. So seeing the auction status is something like we can discuss a bit later. So, and for the entities, apparently we will need like auction. We need the bid. And so let's just list these two as of now and go over to the diagram first. And we will talk through the workflow via doing the design. So let's say we have a user. Okay, let's see, this is a client. Client need to go to an API gateway. We could utilize AWS managed API gateway, and it also have a functionality of load balancing. That is something we also need for routing our workload, and probably authentication authorization related things, and rate limiter. Okay. So we want to talk very detail about this part, and we will need some to go over this part and move on to the auction service. So this service is accept auction post. Record to database. Record the metadata for that or particular auction into database. And this service could also so we can basically using this service for bidding as well. Set bid request and record it to database as well. So naturally we need a database. Okay. Over here, let's talk about the data. First of all, we will have an auction table. For sure, it has to be auction ID and as the primary key and the potentially partition key. And let's talk about more of that when doing deep dive. So auction ID, auction start time. Okay, so time, end time, start price, user ID, and okay, probably highest price, status, and etc. Let's zoom a little bit smaller. Okay, so this is the auction table, and we could basically add another table over here, bid table. So of course we need a bid ID and we need the auction ID. So bid price and accepted or not. And the user as well, like who made that bid and the timestamp. So probably some other metadata around it. So far, like we only need these two tables. Potentially we're needing some user profile related tables, but it's not the core entities over here. So let's focus on the auction table and bid table as of now. So for the first functional requirements, the user is posting the auction via the auction service, and the auction service will return some like 200 or like whatever code to the client, say, okay, so your auction has been posted. And whenever some client is making the bid, they are actually also bidding via this auction service. So it's get recorded into the bid table and return to the client and say, okay, your bid has been accepted or denied. So, okay, so the third one is that the user is able to see the auction status near real time. Okay, so over here, we could basically establish either we could either establish a WebSocket or server-side event to report to the client. Because for HTTP, if we send out those like status via HTTP, we need to send out the headers every time, and it's time-consuming. Not as fast as WebSocket and the server-side events. So for server-side events, it's actually like from server, we send out event to the client side. It's one directional. WebSocket is bidirectional. Apparently, we don't need the WebSocket as of now, because it's just that the server is sending out the message to the client, and the client is not sending back any messages to the server. unless they're basically doing the bid or posting the auctions, which is something different. Okay, so okay, we basically need to go to the load balancer and okay. Auction service. Okay, so I think we could basically okay. Okay, so this is a server-side event. Okay, this is our overall architecture of the system that is basically covering all the functional requirements over here. So let's do the deep dive. So first of all, we need it to be like the third non-functional requirements that we already talked about is posting the auction status near real time. We utilize server-side events to do that. And like in order to make it low latency, so and accepting high throughput of bidding, so we and make sure it's all it's relatively fair bidding for customers, for users, bidders. Okay, so in order to make it a high throughput with relatively fair, so we could introduce a message queue over here. Okay, so for message queue, we have basically two options. One is using a log-based message broker like Kafka. Another option is to use a in-memory queue like AWS SQS to do this. So I would prefer to use Kafka because a couple of reasons. One is that so Kafka is helpful when we want to keep the ordering of the messages. For example, if we want the clients that is sending request to the auction service, and we want to make the process fair enough for all the bidders. For example, like bidder one is submitting that bid with the same price as the second client. So we want to make sure that the first client with the bid process the message and get that bid accepted or denied first before the second one. So Kafka allows us to do that, and unless we, so Kafka is better over here because if we want Kafka to be, let's say, partitioned via a auction ID, so and the consumer, which is the auction service, is partitioning the same way as the Kafka, and the auction service could commit to the offset from the Kafka, and all the messages will get processed in first in, first out order. However, in memory message queue, is actually not having those kinds of order unless we use a FIFO queue, FIFO SQS. So let's just use Kafka over here, and the flow becomes like this. So client goes to the AWS gateway, and it have a small microservices, and we could utilize, for example, like AWS Lambda function, which is a serverless and light-weighted service, allows us to infinitely scale. So in this case, we will send it to the, let's call it producer. Send it to Kafka, and the auction service is the consumer for the Kafka, and they can be both partition by auction ID. Okay. Okay, because of this, we're actually partitioning via auction ID. Our auction service is becoming a stateful service. So stateful means it actually hosting a different set of auction for different auction service. And also because of the client is establishing the server-side events with the service, it's also hosting the client information, and that's why it's stateful. And stateful service, stateful database. because we also, for the database, we also want to partition via auction ID. And so in this case, we can use consistent hashing for the auction service. So, okay, overall, like, we will need a zookeeper that is listening to the managing the could be acting as a coordination service and the naming service, tracking the heartbeat, tracking the failures, and tracking the state for the auction service. So those services is partitioned via auction ID and managed via zookeeper. So, okay. Let's say if one of the auction service, let's say we have multiple different auction services and we have a backup service, we could basically use a state machine replication to do the replicas for our auction service. And the consistent hashing is also maintaining replicas for within the hash range, and that makes sure we are basically having fault tolerant whenever the service is going down, and zookeeper will get to know that, and all the client needs and the SSE server side event will be breaking from that failed server, and the failover will route to another replicated auction service to send out events to the clients. So that is all manageable over here. Another thing is that our database could be utilize a MySQL database, and the MySQL database, I mean, there's a little bit of a relation over here, and the data is pretty structured. And the relational database like MySQL is supporting B-tree structured indexing. So for like looking up a particular ID, so we could utilize a single leader replication, and let's say, for example, we have a leader that is accepting the rights, and the two other, or like a couple of replicas to make sure we have availability and the durability of the data, availability of the service, and the durability of the data. So, okay, and we talked about the like how we want to make the system high available and fault tolerant. Another thing would be so whenever we're using Kafka, and the auction service is potentially we're using Flink as the consumer of the Kafka. So the Kafka and Flink combination make sure that the messages will get delivered at least once. And so because our like we want to make our bidding process as idempotent, and it's okay that like delivering model will be at least once will be matching our goals. So other things I would like to talk about is how do we want to make the process low latency? Because whenever the client is sending out the bid request, they want to know that if their bid get accepted or not. And we want this process to be fast. So how do we want to do that? We have a couple of options. Okay, whenever we decide if the bid has been accepted or denied, the thing we want to check is we want to check the highest price in the auction table. It's just the one simple value versus the bidding value I have. So it's just the one check, and then we could basically decide if we want to update the auction table and update the bid table to see it's accepted or not. So in this case, we could basically keep a key value pair, which is a cache. Let's utilize a cache layer over here. Auction ID. Highest price. Okay. So within the cache, we just need two items. One is the auction ID and the current highest price. So we could basically use a distributed caching, or we can directly use the database cache. And I think whenever we're using a distributed cache like Redis, it's actually adding more workload on the network call because the service needed to check the cache, call the HTTP from the Redis and check first, and then go to database and update the status and the highest price. So instead, if we use a in-memory cache within the database, it would be less load of the network call and make the process even faster. So okay, so yeah, and the decision would be using the database internal cache layer to do the check. So the flow would be, first, I need to check the cache to see if the highest price is actually smaller than my bidding price. If that is the case, then I will need to update the highest price and update the auction table and the bid table. So there's actually a couple of places that we'll need to update. So in order to make it a strong consistency, so how do we want to do that? Of course, you want to, we can basically log the cache and log the database row to achieve that probably, two-phase commit, or like it's not a distributed transaction, but it's actually a transaction that is updating multiple different places. So this is my first option. However, this is because we want to support concurrent bidding for a lot of contentions for a particular auction. So instead, we could use a optimistic concurrent control, and like we could basically utilize something like compare and set. So compare and set is that, okay, we compare, and whenever, but instead of locking it, we first compare it. And whenever we decide to update the database table, we check if the price is matching again before we set it. So by doing compare and set, we could avoid using a role-based logs on our database, and this is a very like a kind of optimistic kind of concurrency control that is making the process of updating much faster and to unblock other incoming concurrent biddings. So yeah, that's the choice we want to go through. So optimistic concurrency and we would like to use compare and set, and we want to use it hash in DB for highest price. And we want to, so we use Kafka plus Flink node at least once deliver with keep ordering, as well as fast consumption. Okay. Low latency of processing of it. Okay. And another thing that we need to do is that let's say whenever we are accepting, okay, so whenever we're accepting a bid, and we could even we could actually even cache the auction within the auction service so that we can fast send it to the client. However, in order to keep this cache and the DB and the cache into auction service sync, it's a little bit of a different, it's a little bit difficult. So we don't go that route because that is adding more load on distributed transaction needed in order to keep the cache and the database data in sync. So we won't go to that route. The user could be able to allow some latency when we are reporting back to the client and see, okay, your bid has been processed with acceptance or denial. So because we already had these kinds of optimization in order to make our processing a little bit faster. Okay, that's all I have. I have covered the functional requirements and the non-functional requirements. So yeah, that's it. Thank you for listening.